All right, so this is going to be our first video that has actual real mathematical content in it. This might be a little bit of a review, especially if you've already taken a class in Calculus 3 or linear algebra or had any sort of experience with multivariate calculus. Because today we're going to be talking all about vectors, and specifically vectors in R2. Right? So as our formal definition, we're simply going to call a vector, or specifically a vector in R2, is going to be an ordered list of two numbers. And these are real numbers, so they can include things like 1, 2, 3, 4, 5. They can be numbers like 1/2 or square root of 2 or pi, but not imaginary numbers like I. We'll save those for another day, honestly, another class. So this is our formal definition. It's simply going to be an ordered list of two numbers. Now there are many different ways to think about vectors, right? It can represent a point in R2. That's just our two-dimensional space or our xy plane. Or we can also think of it as an arrow drawn in R2 with a certain magnitude and direction. And we're going to talk about both of these interpretations in just a second. So as an example, just slide that over there. Right, so as an example, if we consider an ordered pair of two numbers, we can consider this vector, let's say the vector 1 comma square root of 3. Right, this is an ordered list of two numbers, and it's ordered in the sense that the order matters, right? So 1 comma root 3 is different than root 3 comma 1. There are, right off the bat, a number of different ways we can write vectors, and different authors or different classes might write them in different ways. So an equivalent way to write this would be to stack these vectors using square brackets like this, 1 comma root 3. And so for the purposes of our class, we're going to use these two notations semi-interchangeably. Our textbook tends to use this notation, and we'll try to follow that relatively often. There are times when it makes sense to write it in this form, particularly when it comes to something called matrix multiplication, which we'll get to eventually. So we'll use these two notations interchangeably, and what this vector represents can either be sort of two things. It can represent a point in two-dimensional space. So here's my xy plane. Right, and so if these are, so this is 1, 2, 3, this is 1, 2, 3, and then square root of 3 is somewhere between 1 and 2. It's approximately right here on the y-axis. So the point 1 comma root 3 would correspond to the point in R2 with an x value of 1 and a y value of root 3. And so that could be that point right there, would be the vector 1 comma root 3. Right? And in that sense, writing it like this is exactly the same thing as writing an x-coordinate comma y-coordinate. An alternative, and I should say, an alternative way to think about vectors, like we said, is as an arrow with a certain length and a certain direction. And so we can think of it that way by thinking of this vector as the vector that's pointing from the origin to the point 1 comma 3. And for our purposes, we can think of these two objects sometimes interchangeably, or more accurately, it will be worthwhile to think of it in one form in one context and in another form for another context. So the vector 1 comma root 3 is either the point that's floating here, describing the point that's floating here, or describing the vector that's going from the origin out to the point 1 comma root 3. All right, and I should say we will typically denote vectors by using a lowercase letter, so this is a lowercase v, with an arrow overhead. All right, so we could call this the vector v if we wanted to give it a name. And all four of these interpretations is a valid way to think of a vector. All right, so those are some basic vector definitions. All right, And again, an important thing for us to think about is that vectors can be new objects that we can perform some kind of algebra on. In particular, we have definitions for vector addition and for scalar multiplication. And let's remember what each of those are. So for vector addition, we're talking about adding together two different vectors and getting a new vector as our answer. So for example, we could talk about a vector, and I'm going to use, let's see, I'm going to use vector v. I'm going to call this vector 2, 3, and vector w, which I'll call 1, -1. And so we can come up with a formal way to add these two vectors together to create a new vector that's v plus w. And the way that we'll add these vectors together is what's called component-wise. So we'll add their corresponding components together. So v plus w, right, this new vector, formally I could write this as 2, 3 plus 1, -1. But when I add things together component-wise, I'll add the first components together, so that's 2 plus 1, that's 3. And then the second components together, so 3 plus -1, 3 minus 1 is just 2. And so I have this component form of vector addition. Scalar multiplication is defined similarly. All right, so for scalar multiplication, we're going to take a vector and multiply it by a scalar, which is just our way of talking about a number, right, an individual number. So scalar multiplication takes a scalar, a number, multiplies it by a vector, and gives us a new vector as an answer. For example, if I wanted to take the same vector v from up above and multiply it by the scalar 2, I would get 2v, right? That's going to be 2 times the vector, 2, 3. And this will also occur component-wise. By that I mean I will multiply each of these components by the number 2. So this becomes 2 times 2, and then 2 times 3, or 4, 6. All right, so we have our two forms of algebra right now, vector addition and scalar multiplication, and they're each done component-wise. It turns out there's a geometric way to interpret this as well, and I want to talk a moment about that. Right? If I'm going to, let's sort of slide over here for a moment. Right? So if I want to take the same v plus w, I'll see that there's a way to view this visually or geometrically, and let's do that. So if I wanted to draw my xy plane again, right, I could draw my two vectors, v plus w, and so let's do that. V was the vector 2, 3, oh, which means I actually have to go a little bit higher up. Sorry about that. Boop. There we go. All right, so if we wanted to do v as 2, 3, right, that's my vector v. And if I wanted to draw my vector w, that was 1, -1. That's this vector right here. That's w. Then v plus w is the vector I get when formally I'm going to take, let's see if this works. I can take this vector here and drag it on up to go sort of tip to tail like that. So v plus w will be the vector that points from the origin to this new point right here. And in fact, we can see, you know, ish, modulo bad drawings, that this vector v plus w is in fact the vector 3, 2 that we said it would be. Right? So we have this visual sort of tip to tail way to add vectors. And we could have gone in the other order, by the way. So we could have gone w plus v and gotten to the exact same point. Right? Scalar multiplication behaves similarly. So if we want to draw, our axes down here, and all right, so if we want to draw our axes down here, we had our original vector, that was the vector 2, 3, or I'm sorry, 2, 3, that was our vector v. That was our vector v. Well, 2 times v, right, what we had previously scalar multiplied down here, will give us this vector 4, 6. What happens visually is that 2v is literally v stretched by a factor of 2. So it ends up getting stretched all the way up here. Right? Oh, and let's go to red for that. So 2v will be the vector that is v stretched by a factor of 2, and it will be at the point 4, 6, right up here. Right? Notice that this allows for some of our usual rules of algebra to work. So for example, 2v is indeed equal to v plus v, which we would hope would be true in any algebra system that we define. Right? So scalar multiplication actually scales or stretches the vector that's part of the multiplication. And it's one of the reasons that we call scalars scalars. So what we have here are sort of basic objects, vectors, as well as basic operations, scalar multiplication, multiplication and vector addition. And what we can see is that there's really two lenses through which we can view this, right? We can see here a sort of more algebraic component or mathematical sort of number crunchy way in which we literally add and scalar multiply component-wise. And then there's also this vector, this more geometric interpretation in which we're thinking of these objects as being geometric objects and watching what happens through this lens of geometry, sort of literally stretching and lining up vectors in this interesting way. The very final thing that I'll say is that vectors are very general objects, right? In the sense that what we've talked about so far can scale to other kinds of vectors, not just vectors in R2. And as momentary foreshadowing, I just want to say that we will be looking at vectors in higher dimensional spaces. For example, vectors in R3 will be, vector in R3, simply going to be an ordered list of 3 numbers. When we get to an ordered list of 3 numbers, we can think of that not as sitting in the xy plane, but in, say, xyz 3-dimensional space, or R3. So some of these ideas that we're talking about, many of these ideas that we're talking about, will scale up to vectors in higher dimensions. So that's all for now. I'll see you next time.